In this video, I'm going to go over how I make mounting holes for things like fans, PCBs, anything that maybe I'm going to 3D print for like a project enclosure, and how to get that as accurate as possible. 3 ways that I have figured out on how to do this in FreeCAD. So for the first example, I have here just a regular computer fan that I was using for a vent system for my resin printer, and I have to design mounting holes that I will put some M3 inserts into, and I need them to be at an accurate space away so I can screw all of them in along with the top with a filter in between that, and so on and so forth. So for something like this, it's pretty easy. If I go back to the Amazon page I bought it on, I can see they have an image along with their product that shows the dimensions of these, all the particular things you might want to know. And what we're interested in here is these screw holes, which say on the image it's about 71.5 millimeters away, give or take 3 millimeters. I'm just going to take them at face value. After all, these inserts have a little bit of wiggle room, I like to say. So we'll just go ahead and do 71.5. So I'll start creating a new body, rename this to fan base, and we'll create our first sketch, which will basically just be the size of my thing that I want to mount onto the project box or board. So actually, let's not do that. Let's go ahead. We will start on our spreadsheet. I'll go ahead and create a new spreadsheet. And let's see, I'll go ahead and get rid of this. Tile it. Okay, so we have our 3D view and our spreadsheet. So what I'm going to do here is I'm just going to do fan, hole, width. And this is square, right? This is a square object. And on the measurements, the dimensions image for this, we can see that they're both about 71.5 millimeters away from each other. Or actually, so we'll go fan hole D for distance, and I will say 71.5, and that's basically all we'll really need. I'll also do one for the fan box size, and it says 80, but I'm gonna go ahead and do 90 just to make sure that our pegs have enough space, including the depth or like the thickness of the wall size for the insert. So that's actually another good point. We're gonna go M3 insert OD for outside diameter, and I will just take this, go ahead and size it up really quick, and it measures about 4.92. So I'm gonna drop that. I usually like to drop that a little bit, despite, you know, the tolerance of the printer, by say like 0.5-ish, give or take, round it down to the nearest 5. So I'll do 4.85 because I measured out 4.92. And with that, let's also do wall thickness, and I'll do 1.5. And that should pretty much be all we need for the fan to build all of that out. So now I'll go ahead and go to my part design workbench. I'll create my sketch. Alright, so I'll go ahead and draw this box first for the base of this. And I'll just make these symmetrical. It's the easiest way to center that to the middle of the sketch. And then make 2 sides equal. And then I'll just take one of these. I actually forgot. We need to go to our spreadsheet. I'll go ahead and close this really quick. Go to our spreadsheet. Select all of our things that we want to alias. And I will go to macro, my recent macros, and I'll use easy alias. And that went ahead and aliased all of these for me, so now I can use it in my sketch. And I'll post a link to that macro in the description. Okay, so we can come here, spreadsheet dot fan box size. Perfect. Now that's all constrained. You can just go ahead and pad that out. I'll go ahead and do 2. Actually, we'll do spreadsheet dot wall thickness. And then I'll add one more here, call it peg height. And I'll do 15. And I'll just go ahead and click my spreadsheet again, peg height, easy alias, and bam. Cool, so let's go ahead and create our first peg now. So I'll just create a hole real quick. Constrain this distance to spreadsheet.fanHole distance divided by 2. We have to divide it in half because of the symmetry, the point of symmetry here, if that makes any sense. So now I'll do pretty much the same exact thing for this. There we go. So that is basically in place, it should be at least. And for the radius here on the actual circle that will be our peg, I'm gonna first do M3 spreadsheet.m3 insert OD plus spreadsheet.wall thickness. And that'll give us a good little padding, like a little buffer for our insert to sit within. And a lot of people recommend doing a chamfer for something like that, so it sits kind of like a volcano. I don't do that. I have faith in my prints for the most part. Okay, so we will change the Z attachment of this to spreadsheet.wall thickness to account for the bottom of our plate here. So that way we guarantee it is at the surface of that and we get our actual accurate peg height that we want from this. So now I will, before we create any pads or pockets, I'll just go ahead and create my next sketch. That will be the hole for this. And I will say spreadsheet.fanHole D divided by 2. Cool. So that should give us an accurate, pretty precise like positioning of that, because basically what we're aimed at more so than the diameter or radius of this is the centering of that. And as long as we have that, we can just make minor alterations to make sure everything else is cool too. So this one we'll just constrain to spreadsheet.m3 insert OD divided by 2. And again, just change the positioning of this. And there we go. We'll just make sure. Okay, so that's my basic outlines for both the pad and the pocket. So now I'll go ahead and create the pad. And we'll say spreadsheet.peg height. That'll give us that. Then we'll come in with the second one, do a pocket. Typically I have to reverse it, but then we'll attach it to the same formula, spreadsheet dot peg height. Cool. So now I will click on the pad and I create multi-transform twice. The first one's usually always good, so the vertical sketch axis, and then this one change it to the horizontal, and that'll create our 4 pegs. And then I'll do the same thing for the pocket. I'm not sure if there's an easier way to transform like 2 different operations at once, so this is what I'm sticking to for now. And as you can see, there we go, we have our fan base that we will test out in just 1 second. I'm just going to go ahead and round these corners so that they're easier on the printer. There we go. Okay, so that's method number 1, just looking at the data sheet for your object that you're trying to mount. Alright, for our next method here, we have this PCB here that I'm going to demonstrate. I also got it from Amazon, but unfortunately it only shows you the distance from edge to edge of the PCB and not for the holes. So in order for those inserts to sit in there accurately, we'll have to do a little bit of measuring ourselves. Now I did measure these edges beforehand and they are 70mm by 90mm. So the next thing that we have to figure out is how far out these holes, the edge of the hole is from this PCB and the diameter of that itself, and then we can just subtractively make sure that this ends up in the right place. So let me just go ahead and set up the names that I'm going to need here. So the first one will be the green PCB. We'll say width, and then just so we're on the same page here, I will be drawing it this way. So the vertical side is the longer side, and that will be the length. So the PCB width will be 70. Length is going to be 90. And then I'm going to set up a couple others here, such as, so I'll just say offset Y, which will be from here to here, like the spacing between these edges, which seem to be about 1.75 give or take. I'm doing this really roughly, which is why it's varying wildly, so about 1.75. And the next one we have will be the green PCB offset X. That'll be this side, which I kind of measured in at 0.8 give or take. So I'll do 0.8. And the next measurement we're going to need is going to be the diameter itself, which measures at about 3.25. Alright, and with all of that, we can start to calculate our actual distances from the edge of the board to the center of the hole. So if I go here, I'll do easy alias. Okay, so then I'll do green PCB hole underscore Y, which again is going to be that vertical distancing from the edge of the board. And we'll do up here on the content just so it's easier to see, equals, and that'll be green PCB L divided by 2, because we're going to do it from the center here, minus green PCB offset Y minus green PCB hole outer diameter divided by 2. That'll give us this number right here, 41.63, because what that's doing basically is it's taking the length of this, and I explained earlier, since our origin is going to be at the center of the board, we want to divide that in half. So now we end up right here. And when we subtract that offset Y, we're getting to the edge between that hole and the end of the PCB. And then we subtract the outer diameter divided by 2, which effectively is the radius, giving us that center right there. And we will do the same thing for the X. We'll say equals green PCB W divided by 2 minus green PCB offset X minus the diameter divided by 2 again. We get that number. So last thing we'll do is easy alias those. You noticed I like actually using the names of the aliases as opposed to like something like B10, just because it makes it easier for me to understand what's going on in the equation instead of having to reference every time. Alright, so now we can create our new part. I'll call this the green PCB base. We'll create our first sketch again for the bottom plate. However, this one I'm going to do a little more arbitrarily because I already have the width and length defined as these actual lengths from the PCB. So I'm just going to go ahead and add 10 to each one. So for this one, for the width, I'm going to do 80 millimeters. This one here, I'm going to do 100. And you know, ideally for your enclosure, you would already have this size set. I'm just doing this because it's easier for the demonstration. Okay, cool. So we have that. We can close that now. And let's go ahead and make this the wall thickness. And we will go ahead and create our first sketch for the outer perimeter of the insert. Go ahead and size that there. This one will be the spreadsheet green PCB offset Y. Oh, just kidding. Hole Y. And this one will be green PCB hole X. And there we go. That looks pretty good. Now we'll just constrain this to the insert divided by 2 plus the wall thickness. Move it up on the z-axis by the wall thickness. And there we go. We have the outer perimeter. Now we're just going to create the sketch for our inner pocket. And let's see, so go here, and we're just going to do basically the same exact thing. Oh, and I did the exact same thing for the offset. This is going to be hole. And then just make sure that you divide that by 2 because I'm using the radius tool. Well, the radius constraint. You can do the diameter, which I probably should do since I do that so much, but we'll have to wait to do that. Spreadsheet dot wall thickness. There we go. So we have our similar setup again. So now we can just take this one, pad it by the peg height, take this one, pocket, reversed, peg height. There we go. So, and since these holes I measured at roughly the same distance, it should be no problem now to do the same transformations. Alright, cool. So that's method 2, and we will find out if that works. And that brings me to my last method, which is this PCB right here. You will notice has some kind of awkward spacing here and here, and on these edges and these edges. So if I were to just go ahead and measure this out really quick, we got almost 3 millimeters of space between that side and 1 millimeter. So that's about a 2 millimeter difference, right? So if I were to space everything using the last method according to this, the inserts here would end up a little bit farther than the holes here. And if, vice versa, if I were to size them up to here, these would end up a little bit too short. And that's where this method is actually, I don't know if I already mentioned it, but it's easier than the one that we just did because I think you take a lot less measurements for what it's worth. And you actually don't need to take into account the measurement of the board at all. So in order to do this one, basically, we take a measurement in between these holes, and then we take a measurement of the hole itself. And those 3 measurements actually. So yeah, it'll be the x-axis, the y-axis, and then the diameter of the hole. So let me go ahead and start to build out my spreadsheet, and I'll say tan PCB hole distance x, tan PCB hole distance y, and then we'll say tan PCB hole ID for inner diameter. And I guess that should have actually been ID2, my apologies. But yeah, we'll take the X distance now. Looks like about 61.2 millimeters. Okay, so now let's go for the Y. That looks to be about 86 millimeters. We'll just go ahead and round that up. Then the inner diameter of the hole, we'll say, is about 3 millimeters. Okay, and that really is all we need using this method to build our base. So actually, you know what, I will go ahead and add tan v underscore width, tan PCB underscore height, and since this is 70 by 90, again, I'll just make this 80, 100. Go ahead and easy alias that again. Cool. So now we build our new body. And as we've been doing, we will start with our base. So hopefully this all kind of seems straightforward now. Except for right here, I guess. So yeah, before I do that, actually figured out we'll add some more here. We'll do tan PCB underscore hole underscore x, and then tan PCB underscore hole underscore y. And so for the x distance, what we want to do is the tan distance x divided by 2, right? So again, we're starting from the bottom here and going to the top. So when we divide it by 2, we're getting this section right here. But basically in between the holes though, so it won't end up exactly at the edge, it'll end up somewhere over here. Divide it by 2, which will be between the edge, since we measured from edge to edge of the hole. Now we just need to subtract that radius. So we'll do subtracted by tan PCB hole inner diameter divided by 2. And we'll do the same thing, but swapped out for the y-axis. Divided by the y-axis divided by 2 minus the whole inner diameter divided by 2. Okay, and that should be pretty accurate. So let's go ahead, we'll close our sketch really quick so we can alias this. All right, and let's get these dimensions. So we'll make the insert offset plus wall thickness. Then we'll also do the inner one. And there we go. So now we're just following the same protocol where we will mirror our pads and pockets. Great. And then I'll just go ahead and add some chamfers to this as well. Or I think it's a fillet. So then, just to challenge myself, I wanted to try doing this Arduino right here, which it looks like it should screw down with them 3 screws, but you know, what we're really testing for is to see if the screws will go in the first place. So whether or not they go all the way down is not what's up for discussion. What's up for discussion is, can we make those fit? So as you can see, this is the Elegoo Uno R3, and its spacing of its holes are rather interesting because it's not like exactly a perfect square. This board is very populated, and I guess they just had to fit them wherever they could on the design, which makes sense. So a couple of things to note is, if we look at the bottom side, you know, it kind of gets rid of the busyness. These holes look about level, and these do not. You can see this one is a little bit higher, so we'll have to rely on a couple of different methods that we've learned here in order to actually calculate this and get it accurate, and we'll go ahead and print it and see how we did. So actually a datasheet for this is available online, but it's for the official Arduino, and since these manufacturing methods for the Elegoo and Arduino may not be the same, I could end up with something completely different over there. So we just really want to make sure that it's accurate to this board specifically. So what I'll do is I'll go ahead and measure the overall size of this board. This looks about 53.15. Let me just go over here and we'll say width. Then the height of this, 68.5. I'm gonna go ahead and say. Alright, so how are we going to tackle this, considering it's not going to be as easy as just mirroring it this time? My approach is probably going to be figure out the distance of one of these from the edge, and then the distance of both of them, and then we'll probably have to measure these two separately as well, and then kind of create their own paths, their own sketches. We'll say and these names are going to be kind of wonky, so we'll say top hole X for the distance between one of these edges and the first hole, and then the Y will be for the spacing up here. Okay, and then we'll have Arduino distance. So let's try to get the X here from this edge, getting about 6 millimeters. So I think we'll do that for the X, 6 millimeters. And then the Y looks like about 0.8. Ooh, that's 0.08. And then the distance between the two, (31.25). Alright, so that should give us a pretty accurate measurement from the outside of that one. So if we do the left hole now, say hole L, offset X. And then we'll do, while we're at it, okay, so we've got all those labels made now, so let me go ahead and just measure them up. So this one's going to be for the L, offset X, which is going to be this side here. Looks to be about 0.8 as well. And then the offset Y I will do from the bottom, since that's the smaller measurement I can make, 13.5. And now let's do the right hole. 0.9 it looks like. Let's do 0.9. And then the R offset Y, 12.25. Okay, so that was very rough measurement, but that's because I have faith. And using all of this, I believe we can build our last board. So let's go here. Okay, so we do actually have to do some things here. So we'll say Arduino hole L X Y, and these will be the actual positions, so we don't have to do any calculations on the sketch. Okay. I already used X up there on accident instead of offset, so I'll do PX here. Position Y there. Okay, so for the whole X, we will use equals Arduino W, and we'll have to say divided by 2 minus Arduino whole offset top hole X minus, well, actually don't have that yet, so we'll go ahead and do this, and measures about 3.25. And I'll just go ahead and easy alias that really quick. So for Arduino whole X, we're going to do Arduino W divided by 2 minus Arduino top hole X minus Arduino whole inner diameter divided by 2. Gives us 18.95. Then this one, Arduino height divided by 2 minus Arduino whole Y minus Arduino whole inner diameter divided by 2. I will end up doing some math here in the sketch probably, but we'll get to that part. So we'll do Arduino whole RX, which is going to be equal to, oh, so I did this in the wrong place, oops. Go ahead and move that here. Position distance for that one. Cool. So then for the distance between these, we can do equals Arduino top hole D divided by 2 minus Arduino whole inner diameter divided by 2. And that'll give us, so since the distance here is that, when we cut it in half, we remove that and we shave off the diameter, which gives us roughly where it should be in comparison to everything else. Cool. So then we'll go to the left whole X. Equation for that will be the Arduino width divided by 2 minus the Arduino whole L offset X minus the Arduino whole inner diameter divided by 2. And then for the Y, so we don't need to do spreadsheet, we will do Arduino height divided by 2 minus Arduino whole L offset Y minus Arduino whole diameter divided by 2. And then we're just going to do the same thing for here, except for the right hole. There we go. Let's go ahead and alias this, and let's see if we can't build out our Arduino base. Well, actually this one I'll probably do arbitrary again, seeing as to how I have an actual dimension defined for my width and height. So 68 and 80, or 60 and 80 to compensate for the extra peg space it's going to take up. So we'll go ahead and close that, do that. Just going to go ahead and add my fillets now before I forget. We are going to add the top hole here. Should be top hole PY. All right, that gives us that one. So for this one, the height will pretty much be the same. And I guess here I will make I'll make a reference. Okay, and now that we have that, you can get this and do the Arduino P distance, which doesn't look to be right. So I had to change this hop hole PD from divided by 2 to just straight up this minus this, because the distance between there is right, but it was the edges, and that's why we subtract a whole inner diameter, is to get rid of the halves on each side, if that makes sense. So what I'll do here, cool. And I guess that could have been a point, but no bother. Alright, and that one arguably was the more difficult one. So this one should not have been the Arduino hole, should have been the M3 insert. There we go. So then unfortunately we really have to do the same thing to make the holes on those. Unless somebody could suggest a better method. So I'll go ahead and finish those up. Alright, so that's those. Let me just go ahead and pad them out. Go ahead and create those pockets, and then we will start printing. Alright, so I have all of my boards printed and threaded. So now it's just a matter of seeing how we did with each method. So starting first with the fan, I'm going to place this roughly on top there. Actually, let's do this from the side. There we go, so we got one screw anchored down. Let's go for the diagonal. That'll be our best way to ensure that we have a pretty good fit here. Alright, check it out. So And I don't really actually have to tighten these down with an Allen wrench because I'm just testing to see the spacing, and as you can see, this is sitting pretty good. Alright, but this one was a little easy though. We had access to the measurements between the holes there, so let's go for our green PCB board, where we measured from the edges in and then subtracted the radius of the hole to compensate for that and give us the center. And on first glance, the holes seem to line up. So I'll just go ahead. Oh boy. Alright, so the first screw went in, and then again, test diagonally, because if the diagonal lines up, we know basically the rest of the board should be good. There it is. 2 for 2. The method I like to use, whether the spacing is even or not, is this one, because we take less measurements, right? And then it doesn't matter what size the board is. As long as these are even and these are even, you can do this method and save yourself a bunch of time. Alright, so I'll come in with my screw here. Another perfect fit. Alright, so this one I'm pretty excited for because I've never actually tried to do unconventionally drilled board like this. So I'm going to start with this top center one. And it's not going to sit evenly because there's some big pins on the back, I think directly for this USB port. It's almost directly under that hole, so we'll do our best. Okay, and then let's go for this one. I can't believe I'm saying I think it actually worked, because this was more of a proof of concept for myself. Try to prove to myself that I wasn't just taking my own crazy advice. I mean, that one is a little weird just because I think how this board is elevated. If I straighten it out. Oh, and also the head of the screw. I don't know, they didn't give you enough space to actually really put something here, I think. So, I guess I'll just try to thread this one in here then. While I grab this one and there we go. So this one's a little longer, just so we can actually test this here. But as you can see, all of these holes came out precise, and all the threaded inserts are lined up to the Arduino just fine, using combinations of those methods that I showed you earlier in the video. And that's pretty much it. So I will catch you later.